You wake up in your dorm, you walk 1 kilometer to class, maybe in a straight line or something, and then you travel back and go back to sleep. What was the distance that you traveled? This is the d, right? What is the magnitude of your displacement? It's 0. It's the magnitude of your displacement. So Mia is cycling along a straight stretch of track. Her speed is a steady 12 meters per second. Those are the facts that you know. And it's saying that which of these is not a possible position versus time graph for Mia? Survey says, a lot of people are saying D, which is what I liked as well. So my reasoning here was that, remember, these are position versus time graphs, and you weren't told what direction Mia is going. So speed is kind of like the magnitude of the velocity. It means just how fast you're going, and it's always a positive number. But you could be going towards the origin, you could be going away from the origin, you don't know. And it doesn't, some of these have you being, at a different position at time 0. What you can't be is stopped. The horizontal line means that it's not moving up. So these are position versus time graphs. If it was, you can also make a velocity versus time graph. In which case, if you were doing that, if it was v versus t, I think the only correct answer would be D. This is one that's all about instantaneous velocity. So at what time do these two objects have the same velocity? People like 3 seconds. What I'm thinking is that the velocity is like this instantaneous slope. So I would say it's, for this one it's constant, whatever it is. But for the curved line, at any particular instant of time, 1 second, 0 seconds, it's stopped. 1 second is going, 2 seconds is going a little faster. 3 seconds is going a little faster. 4 seconds is going a little faster. It ends up being kind of going faster than A. So velocity is the slope of a tangent. So what I've drawn there are tangents to the curve. So almost like it was a circle or something. Any point here, you can draw a tangent, and that will be, the rise or run of that tangent will be the instantaneous velocity at that moment in time. So it starts off with a very, very slow velocity, looks like 0 actually from rest, and then it speeds up so that eventually B is going faster than A. So I don't think it's possible that they never have the same velocity, since if you start slower and end up faster, you must have passed through the same velocity. So it's somewhere between 0 and 5, they pass through the same velocity, and that's where you have to kind of estimate. To me, it looks like this slope is sort of around the same around here. I don't know if it was exactly 3, but 3 is certainly the closest answer on this list. If you have a position versus time graph and it's a straight line, what does that mean? Does it mean, if it's a straight line, that the object's not moving, B, the object's moving with a constant velocity, or C, the object's moving with a constant acceleration, which survey says, almost a tie. Let's see, drum roll. I liked B. So my reasoning behind B was, it's sort of a, I don't know, you may have got a little mixed up. So I think that a horizontal line means that the object's not moving. So I guess the meaning of what the word straight is, I just meant not curved, right? So it's not a curved line, then I think B is kind of the best answer. A hockey puck is shot into a goal, and it has the velocity versus time graph as shown. We're going to talk a lot more about graphing everything versus time. So you can graph position versus time. We've done a lot of that. If you take the slope of the position versus time graph and graph that, you get the velocity versus time graph. So this thing on the top is the slope of one of the 4 graphs on the bottom. A lot of people were saying D. Did I like that? I did. So let's go to, what was I thinking? So what I was thinking is that, okay, so first of all, with this one and this one, is that I would say teleportation is not allowed in physics. Do you know what I mean by that? So you can't just jump from one X position to another X position with 0 time. I mean, you can go pretty fast, right? But it would be, if it's a perfectly vertical line on your position versus time graph, that means that the slope is infinity. So your speed is infinity. And there's an important rule in physics is that nothing can travel faster than the speed of light. Not even information can travel faster than the speed of light, or else it violates causality and a bunch of bad things. So forget about those ones. So it's either C or D. So what you've got here is a positive slope. So something that has a positive slope followed by something with a zero slope. So like a horizontal line, right? It's not moving. So it's moving, and then it's not moving, so it's not that one. So I like that one. Is saying, okay, a car starts from rest. Maybe it was at a stop sign, and then it starts, and it speeds up, gets to a maximum speed of 30 meters per second, then it coasts at that speed for a while, coasting, I guess, and then sees another stop sign, slows down, and stops. So I'm going to ask you for those three portions of the motion. If it's speeding up, what is the direction of the acceleration vector of the car? Wow, okay, so I didn't even teach this, and some of you guys have a good intuition. I like that. Speeding up, your acceleration is kind of in that direction, so that your change of velocity goes from 0 to something in the forward direction, 30 meters per second, so that delta V is in that to the right, so your acceleration is to the right. This one says, while the car is coasting, what is the direction of the acceleration vector of the car? And by coasting, I just mean that it's going at a constant velocity, I guess. 0, likey. Okay, so if you're not changing your velocity, then it's the acceleration 0. While the car is slowing down, what is the direction of the acceleration vector of the car? Yeah, to the left. Very good. So again, you guys are getting the right basic idea here. A Toyota Camry can accelerate from rest to 100 kilometers per second in 6.5 seconds. I looked that up. A Porsche 918 Spyder can accelerate from rest to 100 kilometers per hour in 2.6 seconds. So you have to imagine they must have tested this on a track. So the question is, during that test of going from 0 to 100, which car drove the longer distance? While you're working on it, I'll give you another minute, but two hints are that the average velocity is the distance traveled divided by the time interval, and also the average of 0 and 100 is 50. Survey says that the Camry, the Toyota, the slower car goes farther. Well, what I think is that for both cars, you would say, I guess, V average is equal to delta x divided by delta t. So you can solve that out for what you're interested in, which is delta x is equal to the average speed times delta t. So in the case of the Camry, I would say delta x is equal to 50 kilometers per hour, because that's the average speed, times 6.5 seconds. And for the Porsche, the delta x is equal to 50 kilometers per hour because it's not really going faster, it's just accelerating more, times 2.6 seconds. And you can't just times those because the units are all garbled up, but you can see that you're going to get a larger number for the Camry, I think. You are traveling at an initial velocity of 30 meters per second, and then you slam on the brakes, which gives you, I don't know how, but this gives you a constant acceleration, or I guess it's a deceleration. The acceleration is negative 10 meters per second squared. So your velocity starts off positive, plus 30, and then you're accelerating at negative 10 meters per second squared. How far do you travel before stopping? 45 meters, which I really like. You're on an eastbound subway train going at 20 meters per second, and you notice the westbound train on the other track. Relative to the ground, the westbound train has a speed of 20 meters per second. So that's the object, is the westbound train. Relative to you, how fast is it going? What's its velocity? All right, so responses. People are saying A, and that was the one I liked as well. Just really quickly, I would say, let's see if I can cram in the answer here. Your train is reference frame 2. And then I would say the ground, maybe, or the lab frame is reference frame 1. So in that thing, you are eastbound in a subway train, so let's define plus is east. So that the velocity of reference frame 2 relative to the ground is equal to plus 20 meters per second. And then there's a westbound train, let's call this W. The velocity of W relative to the ground is equal to negative 20 meters per second. So the equation on the last slide here, I've got now W's instead of, it's the velocity of the westbound train relative to U is going to be the velocity of the westbound train relative to 1 minus the velocity of the reference frame 2 relative to the ground. So you'd say it's minus 20, and then minus plus 20, and I get minus 40. So what this means is that VW2 is equal to 40 meters per second, comma, west. This is a conceptual question about how velocity and acceleration can work. So there's 5 situations. One of them is impossible. A, an object has a velocity directed east and acceleration directed west. B, an object has a velocity directed east and acceleration directed east. C, an object has 0 velocity but non-zero acceleration. D, an object has non-zero acceleration and changing velocity. And E, an object has constant non-zero velocity and changing acceleration. Survey says E, and the other one was C. An object has 0 velocity but non-zero acceleration. So the one that I like to use for an example for that is, we'll talk more about this, is when something's traveling upwards, and if it goes directly up and then stops at the top of its path, the question is it accelerating? And I would say that it's accelerating the whole time. And well, I guess because there's a net force on it the whole time. The net force doesn't go away just because it's at the top of its path. But there's an instant. It's possible for an instant for C to be possible. So, but C is pretty close. E was the one I liked better. Under what condition is average velocity equal to the average of the object's initial and final velocity? A, this can only occur if there is no acceleration. B, the acceleration is constant. C, this can occur only when the velocity is 0. D, the acceleration must be constantly increasing. Or E, the acceleration must be constantly decreasing. If you answered A or if you answered C, your answer is, in a sense, correct. It is true that if there's no acceleration, then the object's initial and final velocity are the same, and if you add them up and divide by 2, then you get the same thing, right? If it was 5 in the beginning and 5 at the end, 5 plus 5 is 10, divided by 2 equals 5. 3 plus 3 over 2 is 3. That kind of thing. Okay, it's a math thing, but it's kind of the trivial case, and it's not only the case. So it is true that if the acceleration is constant, any constant value, then if you add the initial velocity plus the final velocity, divide by 2, you happen to get what the average velocity is. Pretty straightforward. You got a 600-gram basketball and a 60-gram tennis ball are dropped from rest. As they fall to the ground, assume air resistance is negligible. If that's the case, which of the following statements, 3 statements, is true for the balls as they fall? The responses are the accelerations of the basketball and the tennis ball are the same. It's at 9.8 meters per second squared again. So, same situation. A 600-gram basketball and a 60-gram tennis ball are dropped from rest as they fall to the ground. Assume air resistance is negligible. Which of the following statements is true? So A, the force of gravity is 10 times greater on the basketball than on the tennis ball. B, the force of gravity is the same on both balls. Or C, the force of gravity is slightly larger on the basketball than on the tennis ball. I like to predict here, C. Yeah, 10 times. So where I was showing is that the first question, this idea that the accelerations are the same, we can kind of test it, even, to see if that's really true, by just doing the experiment. In case you don't believe me. 1, 2, 3. You release them from rest, they fall at the same acceleration. I don't know if anybody tried that with the grape and the grapefruit, but it's kind of surprising. But it is certainly true that the basketball weighs more. And so there's something called weight, which in this course means the same thing as the force of gravity. So the Earth is somehow reaching up and pulling on these 2 objects, and pulling them towards the center of the earth. And it pulls a lot more force on the basketball than it does on the tennis ball. So, why do they fall? So the reason they fall the same rate is because the acceleration of an object is the force of it divided by its mass. So when something has more mass, it's harder for it to accelerate. So even though the force is 10 times greater in the basketball, its mass is 10 times greater, and they end up canceling. You end up with the same acceleration. So I toss the ball straight up in the air, and again, it's this, immediately after I let it go, what forces are acting on the ball. So when it's like on its way up, okay? A, the downward force of gravity from the earth, which we call weight. B, an upward throwing force from my hand. C, a small downward force from air resistance. D, an upward inertial force carrying the ball forward along its upward trajectory. Drum roll. Responses are... So a lot of people voted for weight, which I think has got to be true, right? Like it's anything, all of us have the downward force of gravity on us. Upward throwing force of hand got a lot less votes. Small downward force of air resistance and this inertial force. So what I liked were A and C. The idea with B is just that after it's left my hand, I'm no longer applying a force to it. So then the question is, why does the ball go up after it's left my hand? Certainly goes up for quite a while. So what would cause it to do that? So, and this is again where playground physics kind of goes against our intuition a little bit, is that, like I think when I was on a tricycle in the playground, if you're trying to ride through sand or something, you really have to push the pedals to go. As soon as you stop pushing, you stop going. And so there's this idea that travel requires some kind of external force. But that's not the case in physics. If something's moving, this is again Newton's first law, if something's moving at some velocity, it wants to continue moving at that constant velocity unless there's an outside force on it. So with no forces at all, once it leaves my hand, it would just keep going up and up forever. But there are two external forces acting on the ball after it leaves. One is gravity, which slows it down, and the other is air resistance, which also slows it down, I guess. They're both downward. But air resistance is a bit smaller than the gravity, probably. Okay, this is a weird one. What you can imagine is that there's two rocks that have... they're very small or something and heavy, so the air resistance is pretty negligible. Heather and Jerry are standing on a bridge 50 meters above the water. Heather throws the rock straight down with an initial speed of 20 meters per second down. Jerry, at the exact same instant of time, throws a rock straight up with 20 meters per second up. So they both hit the water eventually. One goes up and then hits the water. The other, I guess they're leaning over the bridge. And one goes straight down and hits the water. Which rock hits the water faster? Survey says that there's a slight pressure. So Jerry's rock, which went up and down, got a lot of votes, more than Heather's. But the response that I like, if you neglect air resistance, is C. And let me show you sort of some of my reasoning here. So certainly, this is like the bridge. And down here is the water, right? And Heather is the one who throws the rock straight down. So the initial velocity of the rock is minus 20, and then it'll accelerate with some acceleration is negative 9.8 meters per second squared. So it's going to speed up on the way down. It's going to have some final velocity just before it hits the water. You might use, I don't think anyone cares about the time it takes, so you could use, for example, one of those equations that's V squared isn't it V initial squared plus 2 times A times y minus y0 or something like that. Anyway, you could find that speed. So Jerry throws the rock upwards with 20 meters per second. Well, what's going to happen is it's going to go up, stop momentarily, come back down, and hit the water with some V Jerry. And my feeling is that since you don't care about the time, you could use this same equation for both, where the distance is just that the y has dropped down by whatever the height of the bridge was, which we weren't told, by the way, but it's the same height for both. And it doesn't matter if you use plus 20 or minus 20, minus 20 squared is 4 plus 400. 20 squared is plus 400. You're going to get the same squared for both of the numbers, no matter if they're positive or negative. So you're going to get the same final speed. So this is the nice thing about this particular equation. It doesn't matter what happens in between. If they both start at the same position with the same speed, or same velocity squared, then they're going to end up at that same final position with the same v squared as well. Suppose that an object is moving with constant non-zero acceleration. So A, sort of in this direction. And it's constant. Okay. Which of the following is an accurate statement concerning its motion? In equal times, its speed changes by equal amounts. That's could be true. Unless it turns around, I guess. In equal times, its velocity changes by equal amounts. I like that one. In equal times, it moves equal distances. That's definitely not true. A graph of its position as a function of time has a constant slope. That's not true. A graph of its velocity as a function of time, that has constant slope, but it's not a horizontal line. So the answer is B. And the only other thing I would say if you answered question A is remember that the speed v is equal to the absolute value of the velocity, v with little line on the top. So if you had, for example, this is velocity versus time, and it starts off, there's 0 right there, starts off negative and goes positive, the velocity changes by equal amounts in equal times. If you look at for this graph, the absolute value of that, then it looks something like this. It goes down, hits a 0, and then so it slows down, and then speeds up. And so what we would say is that this speed is decreasing from here to here, doesn't change at all, then it's increasing. So there are different time intervals have different changes in speed. So that is why A is wrong. Question 5. The figure shows the velocity versus time graph for a basketball player traveling up and down the court in a straight line path. So it goes up, positive velocity, and then stops, and then has negative velocity. Find the displacement of the player between t equals 0, which is here, and t equals 6 seconds. So the displacement is going to be delta x is the area under the v versus t graph. So just have to find these areas. So I would say this area right there, maybe call that A1 plus like A2 down here plus A3 and there's A4 down here. So I would say that delta x is going to be A1, which is a triangle, plus A2 plus A3 minus the area of 4. And so I'm just going to use triangle or rectangle rules. So it's A1 is going to be 1/2 base times height. A2 is just going to be the base times the height there. Plus A3 is going to be 1/2 base times the height. And then minus 1/2 the base times the height. They all have different bases and heights, but I'm not going to put subscripts everywhere. It's 1/2 of the base is 3 seconds. Just keep SI units here. And the height from 1 to 4 is times 3 meters per second. Plus, just base times height, that's 3 seconds times its height is just 1 meter per second. Plus, this thing over here, its base is 5 minus 3, so that's 1/2 of 2 seconds. And its height is 4 meters per second times 4. And then minus, this is just a 1 by 1, so it's 1/2 of 1 times 1. So working that all out, I've got 3 times 3 is 9 over 2 plus 3 plus these 2's cancel, so it's 4, and then minus 0.5. So I've got 4.5 plus 7 minus 0.5. 4 plus 7 is like 11, so it's 11.5 minus 0.5, so it should be 11 meters. Delta x
equals 11 meters. E. Question 6. A cart is driven by a fan. So here's the cart. Here's the little fan on the top, which gives it a constant acceleration. So A, again, equals constant. That's good to know. The cart accelerates from V0 equals 36.6 centimeters per second. That's not an SI unit, but that's okay, I hope. To, over here, V final is 94.9 centimeters per second. In the time is 2.0 seconds, and it says how far does the cart travel in this time? We need this. And just to make sure this makes sense, I would say that since it's speeding up, A is in this direction. It's positive. Okay, so this is pretty straightforward. If we look at our equations of constant acceleration, look at what we don't seem to care about here. We need the distance traveled. And what's weird here is we know that A is constant, but we don't care what it is. But we don't care about it. So choose the equation that doesn't contain A would be that last one, combo of equation 2.50 and 2.51 from your text, which looks like x is equal to x0 plus v0 plus v divided by 2 times t. We'll define, I guess, x0 equals 0. So you get x is equal to, that's what we're trying to find here, 0 plus, am I worried about centimeters? These are all in centimeters, so I think I'm just going to not convert to SI units because the seconds will cancel the seconds. We've got 36.6 plus 94.9. I remember those are centimeters per second divided by 2 times the time, which is 2 seconds. So this 2.0 seconds here will cancel the seconds there, and you'll just end up with centimeters. So this should work, I hope. X is equal to, open bracket, 36.6 plus 94.9, close bracket. Well, I think that's really all we need to do, because we're going to divide by 2 and times by 2. 131.5. And that is going to be in centimeters. So closest answer is B. Question 7. From her bedroom window, a girl drops a water-filled balloon 6 meters below. So there's the window, there's the balloon. If the balloon is released from rest, so V0 equals 0. It goes down this distance. This total distance is 6.0 meters. I'm going to define that. How long is it in the air? So T equals question mark. So this is free fall. I'm going to assume there's no air resistance, so I'm going to say G is equal to 9.8 meters per second squared. That's the acceleration. So what I need to do here is define my y-axis. So I think what I'm going to do is going to say that y0 equals 0, and I'm going to put the plus y direction downward, so that a sub y is equal to plus 9.8 meters per second squared. And then what I'd say is that the y final is plus 6.0 meters. There are many ways of doing this question, but and you can define y as up if you want. I have defined y is down. Plus y is down. If plus y is up, then you just get negative acceleration and negative distance. So, and again, what do we not care about? It seems that we don't care about the final velocity just before it hits the ground. I guess it's going to stop when it hits the ground, but just before it hits the ground, don't care about v final. So use that equation that doesn't contain v final, equation 2.53, which is, I'm going to convert it to y's instead of x's, y0 plus v0t plus 1/2 a times t squared. We're defining y0 as 0. We've said that the thing starts from rest, so you just see there that y equals 1/2, I'm going to call it g, t squared. Solve for t. Let's just rearrange. 2 times y is g t squared, so 2 y over g equals t squared. So t is equal to the square root, and it'll be a positive number of 2 times y divided by g. So t is equal to the square root of 2 times 6 divided by 9.8. 2 times 6 divided by 9.8 equals square root 1.1066 seconds, and that's closest to E. Last question. A ball is thrown straight upward. So there's the ball. At 4 meters above its launch point, the ball's speed is 1/2 its launch speed. So there's some v0, and then this v here is equal to v0 over 2, and this distance here is 4. What maximum height above its launch point does the ball attain? So there's sort of two parts to this problem. This is the 4 meters climb, and then there's the maximum height, where you'll get v is equal to 0. The final vy is 0. So I think I'm going to split this into two. I'm going to try to find, we need its initial speed, I guess, v0, and then we can plug that in to here. So what I'll do is I'll define y0 equals 0, plus y is up, I guess, easiest thing for this problem, so that now a sub y, the acceleration is negative 9.8 meters per second squared. It's negative g, I guess. And we know it goes 4 meters, so y here is equal to 4 meters. And it seems we don't care about time in this question. So that means we use equation 2.54, which is that v squared is equal to v0 squared plus 2 times a times y minus y0. Again, I've replaced the x's with y's because we're doing vertical motion. Okay, and this, we'll call this a sub y. So, and then we know that the final v is just equal to v over 2. So it's going to look like v over 2 all squared equals v0 squared minus 2 times g, because I've replaced a with minus g. A sub y equals minus g. And then y0 equals 0, so this is this 4 meters y. And what are we trying to do? We're trying to solve for v0. How do we do that? Well, let's square this stuff on this side. So v0 squared divided by 4, because 2 squared is 4, is equal to v0 squared minus 2gy. I think I'm going to have to go over here, use some of this paper. I would say v0, so let's get all the v0s on one side of the equation. v0 squared over 4 minus v0 squared is equal to negative 2gy. Maybe we should find a common denominator here. So v0 squared minus 4 v0 squared, both over 4, is equal to negative 2gy. So I got 1 minus 4 is negative 3. v0 squared over 4 equals negative 2gy. So v0 squared is equal to, I guess we'll just multiply, I got 8 over 3gy. So v0 is equal to the square root of 8g times y over 3. Square root of 8 times 9.8 times, what was it, 4 meters, 4, divided by 3, 8 times 9.8, if I can read my own handwriting there, times 4, divided by 3 equals, take the square root of that. So the initial speed is 10.224 meters per second. So now I use that, v0 is equal to 10.224 meters per second. I know that from this first information, and again, v's final is 0 because it's reached its maximum height. What we need is y, and again, we got A is negative g, and again, don't care about time. So we're going to use that same equation, t, so that's equation, again, 2.54. We get that v squared equals v0 squared plus 2a sub y minus y0. And we're going to solve for y. Hopefully we have enough room to do that. Remember, v is 0, so we've just got negative v0 squared is equal to negative 2g times y. This one is 0 as well. And then the negatives cancel both sides, and I get y is equal to v0 squared over 2g. So it's going to be 10.224 squared divided by 2 times 9.8. 10.224 squared divided by 2 equals, divided by 9.8 equals 5.333 meters, which is closest to B.